My name is Ryan Gaminis, and I am here today to tell you about the UCHS Electronics Club and our latest project. The Electronics Club was established in September of 2019. Our goal is to educate our fellow students on the many aspects of electrical engineering and provide a space for students to collaborate on projects they are pursuing. A recent project of ours was using a quadcopter to carry radio equipment capable of tracking weather balloons. Twice per day, in 92 locations across the United States, the National Weather Service, NWS, launches weather balloons. Here you can see a map of the Weather Service's sites. These devices consist of a helium or hydrogen-filled balloon. Attached to the balloon with twine is a parachute and a radiosonde. A radiosonde, as shown here, is a single-use instrument that transmits GPS position, altitude, atmospheric pressure, temperature, and relative humidity as the balloon carries it into the atmosphere. This data is collected in real time during the ascent by a designated monitoring station and used to predict weather and model wind patterns, as well as provide critical information to aircraft. There are several models of radiosondes used by weather agencies around the world. The two main manufacturers are Vaisala and Lockheed Martin. In the US, Vaisala's RS-92 NGP, RS-41, and Lockheed Martin's LMS-6 are the most popular radiosondes. The National Weather Service stops tracking the radiosondes once the balloon bursts and does not attempt to retrieve them. As a challenging academic project, we went about setting up a radiosonde tracking system that would assist us in the recovery of the sondes. To receive the radio signals and turn them into something we can work with, we use an RTL-SDR software-defined radio. These are quite inexpensive and can be used for a vast range of projects. The RTL-SDR is connected to a Raspberry Pi running Linux. The Raspberry Pi runs an open-source program called AutoRx. Designed by Mark Jessup, AutoRx performs automatic detection and decoding of radiosondes. After the data from the radiosonde is decoded, it is uploaded to a website called SondeHub, where the user can view the radiosonde's location on a map and see live landing site predictions. Using this setup as it stands is effective, and we have been able to recover a couple of radiosondes using it. Here are a couple of our finds. This first radiosonde landed in the mountainous areas south of Ramona, California. It was an especially tricky recovery due to the high wind and amount of mountains that blocked the radio signal. This radiosonde was found in starkly different terrain. Landing mere walking distance from the USA-Mexico border, it had touched down in the desert east of San Diego. What we noticed during both of these recoveries was that the signal from the radiosonde was quickly lost once it reached a low altitude. This was quite an issue as it can drift very far at this low altitude before finally landing, thus making our search area much larger. A brief word on radio horizon. When you are working with high-frequency signals, they cannot pass through most terrain and do not reflect off the atmosphere, so they are limited to radio line of sight. There is a helpful diagram depicting the concept shown here. Back to our issue. When the radiosonde drops below the radio horizon or is obstructed by land features, we lose the valuable signal. We cannot control the location of the radiosonde, but we can control where our receiver is. We decided to attach the receiving equipment to a quadcopter that would carry it above the radio horizon where it can continue to receive and decode the signal. After some planning, a set of requirements were developed. The quadcopter must be capable of carrying a significant payload, fast, durable, fly on open-source software for integration with the receiver, and well documented. These requirements led us to an FPV quadcopter. While absolute speed and precision was not a concern, the expandability and expansive options for components made it a good choice. The quadcopter we decided to use was courteously provided by HobbyKing. The frame is a Diatone Tyrant 215 paired with some Turnigy 2206 2600 kV motors. and driven by a Razor 40 amp ESC flight controller combo. The quadcopter did not come pre-built, rather a fair bit of assembly was required. Each of the motors must be soldered to the electronic speed controller. Then, the video camera, video transmitter, and receiver each must be connected to the board via some helpful connectors. Once the quadcopter is assembled, the flight controller must be configured for the specific components and layout. This is done by connecting the quadcopter to a computer and using the Betaflight configurator. Here we set, among other things, the layout of the motors, receiver type and interface, and controller switch and mapping. If you'd like to learn more about this, there are many good tutorials available online. Attached to the quadcopter is a Raspberry Pi 3B Plus and RTL SDR Blog version 3 dongle. We chose the Raspberry Pi 3B Plus because of its capable computing power and inexpensive price. Since the odds of it getting destroyed in a crash are not insignificant, the cheaper price is definitely an advantage. For the radio, we also went for inexpensive and effective. The RTL SDR is a widely known, cheap, software-defined radio. It is also supported by the software we will be using. The quadcopter is controlled with an FrSky radio controller and flown with an FPV video feed. There are two common flight modes, self-level and acro. In self-level, the quadcopter flies much the same as most larger photography rigs, in that if you let go of the sticks, the quadcopter returns to a level position. In acro mode, the quadcopter can be set to any orientation that the user wishes and will stay in that position until further input. As we are not looking for the precision equated with acro mode, we use self-level for all these tests, as it is significantly easier to learn to operate. In order to power the Raspberry Pi, we used the flight controller's integrated 5-volt regulator. This worked for our testing, but may pose issues in the future if we run more power-demanding hardware, as the board can't deliver too much current. The Raspberry Pi on the aircraft uses the same onboard software as our base stations to decode and process the radio signal. To get the data back down to the ground station, a 2.4 GHz Wi-Fi network is created from the ground and ported to a cellular phone for internet connectivity. This lets the Raspberry Pi on the quadcopter immediately upload the data to the Sonde Hub server. The advantage of this is that other participants in the chase can see our data and utilize it in recovery. Here's the quadcopter taking off and landing while carrying the radio equipment during an active Radiosonde flight. While flying the quad with the payload attached, it is very evident that the motors were under more load, although multiple temperature checks ensured that they were not near burning out. Handling of the quadcopter was also affected. It was not as fast and responsive as could be expected. However, it still exceeded our expectations. The radio equipment worked as intended while attached to the quadcopter. You can see that, while the signal strength fluctuates, it is still strong enough to be decoded. And here's a quick snippet of the live preview map, although with a different Radiosonde. With this preliminary testing completed with no significant issues, we began to look out for a Radiosonde that would be landing nearby. To choose the day that we go out on a hunt, we use the CUSF landing predictor. The landing predictor uses user-inputted information including the launch site, estimated ascent and descent rates, and estimated balloon burst altitude. The software then uses NOAA wind models to predict where and when the Radiosonde will land. These predictions are relatively accurate and give us a good clue as to whether or not it is worth attempting to recover a particular radiosonde. We use this website to decide on a day to test the quadcopter. When the day came, we packed up our chase vehicles, charged batteries, and ran final predictions to establish general driving routes. Each car had a driver and co-pilot. The co-pilot was in charge of operating radio equipment, navigation, and communicating with the other chase team members. As per schedule, at precisely 4:15 p.m., the balloon was released by the automated launcher at Miramar Air Force Base. The duration of the flight is approximately an hour and a half. This depends on conditions and the presence or lack of a parachute on the sonde assembly. Here's a video of the quadcopter being deployed mid-hunt to pick up the radio signal during the radiosonde's final descent. After taking off, we continuously moved the quadcopter around while watching the received signal strength to find the sweet spot where the signal was the strongest. As the radiosonde landed, we were able to clearly receive the signal thanks to the quadcopter. The particular radiosonde landed in a field of windmills. Fortunately, it didn't get snagged on the way down. After a short hike off the beaten trail, we found our treasure. Our future plans for this quadcopter include a couple more projects. First, we would like to put 4 antennas on extended arms and run a Kerberos SDR on the quad. This would allow us to find the angle of arrival of radio signals. Paired with a GPS unit, we could fly around and take various bearings, triangulating a radio signal even if it doesn't transmit its location. We already have the hardware for this project and have been testing it out on the ground with success. The third project that we have planned for this quadcopter is using it for thermal imaging of buildings to detect HVAC leakage. The quadcopter will carry a long-range thermal imaging camera and a GPS unit. By searching the perimeter of a building's windows and possible vents during a cold day, the camera would be able to see any heat leaking out and thus identify areas of improvement to aid in building efficiency. If this was refined to an easy-to-deploy tool, it could quickly become an aid for many HVAC inspectors and engineers. The HobbyKing quadcopter has proved to be a valuable and versatile tool that we will be able to use as a base for multiple interesting projects that will challenge our students academically and assist us in making contributions to the scientific community. If you'd like to learn more, you can contact us at the email on the screen or follow our media manager's Twitter.